Hello everyone, good evening. Welcome to the course of Nanotechnology, Science and Application. The course coordinator for the course is Professor Pratap Haritos from IIT Madras, and I will be the teaching assistant for this course. So this is a 8-week course in NPTEL, which is designed to introduce you to the world of nanotechnology and nanomaterials, its science, and finally its application, like where are we using nanomaterials, how nanotechnology can be used to engineer nanoparticles or nanomaterials. So we'll be looking into that in this 8-week course. This is the first session of this course. So in this session, I'll be introducing you to the nanotechnology. What is nanotechnology? What is nanomaterials? How are they related to each other? What is the production mechanism of nanomaterials? Then finally, I will be covering the types of nanomaterials and the classification of nanomaterials. And let's begin the course. This is a slide to just give you an idea about the different sizes of materials we use in our daily life. Starting from the tennis ball, which is around 10 to the power 8 nanometers in diameter, then coming down to around 10 to the power 4 to 10 to the power 5 are the cancerous cells, are the biological organisms like viruses, bacteria. They come around 10 to the power 2 to 10 to the power 5 nanometers in diameters. Then finally comes the glucose and the antibody, which are around 1 to 10 nanometers in diameter. Finally comes the water molecules. The water molecules are quite smaller than the nanometer range. They are around 10 to the power minus 1 nanometers. So we will be working basically around uh, things, that is 1 to 100 nanometers in diameter range, which generally includes uh, the biological organisms, as you can see, as well as metallics and nonmetals. Then let's focus on the definition of nanomaterials. What is nanomaterials and all? Um, the classification of nanomaterials I will be covering in the next half of the slide. In the first initial slides, I will be introducing you to the nanomaterials. In the first, there are different varieties of nanomaterials such as fullerenes, nanotubes, graphene, graphite, diamond, and for, as you can see, these are the examples of nanomaterials. But let's first introduce what nanomaterials are. There are small videos which I have included in this presentation, which can help you to get an understanding of what nanomaterials are. Then finally, we will be defining the definition of nanomaterials. Hope you enjoy these videos.
At a first glance, nanoscale materials may seem to exist in an exotic world all to their own. After all, nanomaterials tend to behave radically different. At a first glance, nanoscale materials may seem to exist in an exotic world all to their own. After all, nanomaterials tend to behave radically different from their corresponding bulk materials, even though they have the exact same chemical composition and are made of the exact same types of atoms. For instance, the atoms that make up a gold bar are identical to the atoms that make up a gold nanoparticle. In our everyday lives, we're used to objects having consistent and fixed properties when their chemical compositions are consistent and fixed. For instance, regardless of their size, shape, or function, identical materials will appear the same color, have the same conductivity, and melt at the same temperature. So why are things so different at the nanoscale? The most obvious characteristic common to all nanomaterials is their nanosize. They are composed of a relatively small number of atoms and typically measure under about 100 nanometers. As it turns out, when an object is composed of such few atoms, unique phenomena occur which overpower the effects of classical physics. So at the nanoscale, it isn't just a material's chemical composition that determines its properties, For example, small changes in the size and shape of a nanomaterial can result in unexpected and unpredictable behaviors compared to larger bulk objects made of the exact same material. The shape and size dependence of these properties is an important characteristic unique to nanomaterials. Another unique characteristic of nanomaterials is that they take up a much smaller volume than their corresponding bulk materials, but by comparison, also have a much larger surface area. Additionally, certain nanomaterials can disperse well in solution even when their bulk counterparts would sink under the force of gravity. Nanomaterials can even interact with light in different ways, including taking on new colors. The uniqueness of nanomaterials and the ability to manipulate them is what makes nanotechnology so diverse and exciting. Scientists can tune the composition, size, and shape of nanomaterials to engineer something completely new with the ideal properties for any given application. Let's take a look at the element silver. For hundreds of years, silver has been used to make coins and jewelry. No matter what it's used for, all forms of pure bulk silver behave the same way and have the same properties, like its characteristic metallic luster. In stark contrast, silver nanomaterials exhibit entirely new and unique behaviors and properties. Tiny clusters of silver can have antimicrobial properties, which can be used to create bacteria-resistant clothing or more effective mouthwash. Two-dimensional networks of tiny silver wires can retain high conductivity while acquiring new properties such as flexibility, stretchability, and transparency, which can be used to make foldable touchscreens or printable electronic displays. Ultra-thin films or layers of silver can similarly be utilized in high-efficient solar cells. And that's just one element. Imagine what we can do with all the other elements and their combinations when engineered at the nanoscale. Just like that, it's as if the periodic table expands into new dimensions, opening up a whole new universe of possibilities.
Okay, as I said,
Yeah. You got an understanding of what nanomaterials are and what are the properties we can get by engineering the nanomaterials or the engineering the particles at a nanoscale. We always initially conventionally we always think that the properties of the materials depends on the chemical composition of the material. uh, Chemical composition of the material, if the chemical compositions are uniform, the properties will be uniform, but that's not the case. We can engineer a material according to our requirements at a nanoscale. That's called nano engineering or called nanotechnology. And the nanomaterials are the materials whose dimensions are in the nano range. Let's watch another video to get a feel of what nanoparticles are.
Hey, do you know what nano means? It means small, very small. It is 1,000,000 times smaller than the smallest measure on a ruler. If you want to get an idea of how small a nanometer really is, you'll need to take a piece of hair from your head. Go on, it won't hurt. Got it. Now take a good close look at that strand of hair. Not much to look at, is it? If we were to shrink you down, smaller than the smallest thing you can see with the naked eye, you will find that your piece of hair starts to look a lot more interesting. You are now about the size of a red blood cell. Your strand of hair is a massive tree compared to you. Even at this size, you're still about 1,000 times too big to be considered nano. To get you down to the nanoscale, we will have to shrink you to about 100 nanometers tall. Hey, where are all the lights? You are now smaller than the wavelength of visible light. You are practically invisible. But for the sake of demonstration, I think we should turn on some lights. At this size, the red blood cell is 1,000 times bigger than you are. It is like an enormous stadium. Welcome to the nanoscale. You could probably hold a common cold virus in your hands quite comfortably now. The rhinovirus is only about 30 nanometers across and is nearly impossible to see next to the red blood cell. A red blood cell is too big to be considered nano. However, it's made up of all kinds of nanomaterials. If you were to look close enough, you would see that the outer walls of the cell are stabilized by a flexible, mesh-like protein skeleton. The bars and connectors that make up this mesh are considered part of a nanomaterial. Without these reinforcing nanostructures, the cell would be much more fragile and not nearly as flexible. It wouldn't stand a chance in your body. Everything is made up of nanomaterials. Nanomaterials are an arrangement of molecules and atoms that, when combined, create stable building blocks that can be made into larger, more complex materials and structures. Which is pretty much everything, including this little piece of hair. I bet you didn't think there was so much going on in such a small amount of space.
Yeah. So these two videos, I hope these two videos gave you an idea of what range were you talking about when we talk about nanomaterials. It's 10 to the power minus 9 meter. That's like very less. It's as seen in the video, it's like smaller than the red blood cells which are present in your body. So one more statement was there in the video that all materials are made of nanoparticles. Of course, all materials are made of nanoparticles because we know we are made of atoms. Then nanoparticles, atoms are at 10 to the minus 10 meters. Then comes the nanomaterials 10 to the minus 9 meters. Then comes the macro scale, which we are in of. That doesn't mean that we are all nanomaterials. That means the definition of nanomaterials uh, is different. We are all made of, though we are all made of nanoparticles, though we are all made of nanomaterials, we are not considered as nanomaterials. So the definition of nanomaterials is any one dimension of the part of the material should be less than 100 nanometer. Then it can be called as a nanoparticle or a nanomaterial. Though we are all made of nanomaterials, but we are not considered as nanomaterials because the definition lies in that at least one of the dimension of the particle should be less than 100 nanometers. And here this tree uh, shows you the different applications of nanomaterials. As you can see, there are wide varieties of applications of nanomaterials. This shows that this shows that the nanomaterials can be used everywhere, like in case of biosensors, supercapacitors, the hydrogen storage, coatings, electrolysis, in every aspect such as chemical engineering, mechanical engineering, every aspect we are using nanomaterials. Then comes to the history of nanomaterials. The history starts with Richard Feynman and his words, there is plenty of room at the bottom. He he had a wide dream about he had a wide dream about that in the macro scale. At that time there was no instruments to see the nanoparticles, but he knew that macro scale is not the one which we need to look at. We need to go beyond that towards micro scales and beyond that towards nanoscales. So finally, the invention of scanning tunneling microscope in 1991 and the discovery of fullerenes in 1985 gave rise to the significant significance of nanomaterials and nanoparticles. Then comes the classification, or what are the different types of nanoparticles, or what are the different types of nanomaterials known. First comes the naturally occurring. Naturally occurring, you mean they are available in the nature. They are not man-made or they are not created by any other living beings. They are naturally present. Here, in these naturally occurring nanoparticles, in nanomaterials, there is an example of smoke, volcanic dusts, and bacteria. These are naturally occurring. They are in the they are all in the size of nanoparticles. At least one of the dimension is less than 100 nanometer. Then comes man-made. How we are making nanoparticles. The man-made ones are classified into two more types. One is incidental ones. That is, incidental means it is created as a byproduct of a reaction. The intended reaction, the intended product of the reaction is different. We are not creating the nanoparticle in this, but it is a byproduct of the reaction. That is called incidental. We are producing something, but we got nanoparticles. The examples are diesel exhaust, coal combustions, and welding fumes. Then another sector of man-made nanoparticles is engineered, that we are manufacturing. Our aim is to manufacture nanomaterials and we are manufacturing them. That is called engineered nanomaterials. The examples are nanotubes and fullerenes. So this is just a basic classification of as according to occurrences of nanomaterials. Then there are various other classifications, such as on the basis of origin, on the basis of dimension. On the basis of dimension, as I showed you in the first presentation, first slide, there are four dimensions. That is zero dimension nanomaterials, one dimension nanomaterials, two dimension nanomaterials, and three dimension nanomaterials. The definition of nanomaterial says that at least one of the dimension is in nano range. In zero dimension nanomaterials, all the directions x, y, and z axes, the nanoparticles are in the nano range. That is less than 100 nanometer. That is zero dimension. In one dimension, that is a cylinder. Like there are three axes, x, y, and z axis. Let's suppose the z axis is the length of the cylinder. That is not in the nano range, but the other two axes are in the other two axes are in the nano range. And according to the definition of nanoparticles, at least one should be in the nano range. So they are considered as nanomaterials, but one of the length is not in the nano range. That's why they are known as one dimension nanomaterials. Similarly, two dimension nanomaterials. Two of the axes are not in the nano range. The others are in the nano range. And three dimension nanomaterials, then finally comes the three dimension nanomaterials. Um, then the classification is also on the basis of compositions. They are polymeric, lipid, and inorganic nanomaterials. They are mostly biological based nanomaterials on the basis of compositions. Then this was all about the classification. Then comes the synthesis. How are we producing this nanomaterials? What is the production techniques, or how are you manufacturing them? Because they are such small materials. They are in the range of 10 to the power minus 9 nanometers. How are you sorry, 10 to the power minus 9 meters? How are we manufacturing them? Let's watch some videos to get an idea. As you can see in this video, there are two different approaches. One is bottom up approach and one shows top down approach. The top down approach, that means you are in the top of the scale, you are in the top of the scale bar, and then you are coming to the bottom of the scale bar. Let me show you the scale bar once more to give you an idea of what I'm talking about. As I mentioned in the first slide, this is, here you are in the top of the scale bar, then you are coming to the bottom of the scale bar, that is in this range, in the nanometer range. So how can you do that? One method is by breaking them, breaking the particles which are in this range to in the particles in this range. That is called top-down approach. Examples will be, as you can say, mechanical grinding or ball milling. Because in case of that ball milling or mechanical grinding, you are taking a material in the micron range or a macro range, that is by 8 nanometers, and you are breaking down into the nano range. Then another approach, the second approach which we saw is that the second approach which we saw was that the bottom up approach. The bottom up approach is that, which means it's the totally opposite of top down approach. From bigger particles, we're breaking down into nanoparticles. But in bottom up approach, what we are doing, we're starting up with smaller particles, such as atoms and molecules, and we're growing them to produce nanoparticles. Because atoms and molecules, they are in the range of 10 to the power minus 10 meters. That is quite in the range of angstrom, which is even lesser than nanoparticles. And we are growing them to produce nanomaterials. This is known as a bottom-up approach. So, for example, where in the scale where we are talking about, here we are in the scale. Here we are in the scale, in this range, in atomic range, and then we are growing. We are growing in this. We are growing the particle to this range. That is in the nanomaterial range. So, what are the synthesis techniques we learned about? There are two types of synthetic techniques we learned. One is top-down approach and one is bottom-up approach. And in top-down approach, what we learned, particles are in the bigger size range. They are brought down into, uh, uh, they are broken down into particles with nanomaterials. In bottom-up approach, particles are smaller than nanomaterials. They are upscaled to nanoparticles. Let me show you another video to give you some more clarification regarding this synthesis techniques. Uh, this this you can see is a top-down approach of nanoparticle synthesis. Let's see how is it happening.
To synthesize polyanhydride nanoparticles, we begin by weighing the necessary polymer, typically 25 to 100 milligrams, into a glass vial.
In addition, the payload that will be encapsulated is added to the glass vial. In this example, we are encapsulating a fluorescent dye.
Next, methylene chloride is added to dissolve the polymer at a concentration of 20 milligrams per milliliter.
As you can see, the particles are visible to the naked eye. That means they are in macro range or micro range, which are visible to the naked eye. We are breaking them down into. We have to break them down into nano range. That is top-down approach.
To ensure the polymer is fully dissolved and that the payload is evenly dispersed, the solution is sonicated with a probe sonicator for 30 seconds.
Next, we measure the required amount of pentane, the non-solvent, into a Nalgene beaker. We use enough pentane to achieve a 1 to 250 ratio of methylene chloride to pentane.
Due to the low glass transition temperature of the polyhydrides, we add a stir bar to the Nalgene beaker and place it in a liquid nitrogen bath. The temperature is monitored until the pentane reaches -20 degrees Celsius.
Once the appropriate temperature is reached, the nanoparticles are precipitated by pouring the methylene chloride solution into the beaker of chilled pentane.
The precipitated nanoparticles are then collected on a number 50 Wattman filter paper via vacuum filtration.
Once dry, scrape the nanoparticles from the filter paper. We typically recover 50 to 80% of the original batch size. Place the nanoparticles in a microcentrifuge tube for storage. The nanoparticles should be stored dry with desiccant at -20 degrees Celsius or below.
Before use, the nanoparticle morphology and size are verified with scanning electron microscopy.
To prepare the nanoparticles for animal immunization, add sterile saline to the nanoparticles at the chosen concentration. Sonicate the nanoparticles on.
Yeah. So this was a video of how you can produce nanoparticles in a basic sense. Then they finally used it for a biological application, which is not in the scope of this course. We'll be not covering that. So this was just an example to show you how the nanoparticles are being made. So as we learned, there are two types of approaches. One is a top-down, and the other one is a bottom-up approach. The top-down approach is mostly used in industrial production because it's quite cheaper. Because the from material to breakdown from material from a higher size to a lower size is cheaper than handling the materials at a way at a atomic scale. It's quite difficult to handle those materials, but it's quite easier to handle a top-down approach. That's why all the industries focus on top-down approach of nanoparticle synthesis. But the disadvantage of the top-down approach is that because we are breaking down nanoparticles by using different techniques, there is a chance of chemical and surface imperfections on the materials. The nanoparticles which are generated may not be pure. in case of top-down approach. Whereas in case of bottom-up approach, as we are starting from the base material, as we are starting from way below the nano range, there is homogeneity in the composition because all the particles are homogeneous and they combine to form a homogeneous nanoparticles. So that's the difference between top down and bottom up, where top down has a lot of chemical and surface imperfections, whereas the bottom up approach, chemical homogeneity is maintained in the nanoparticles. The examples are mechanical grinding, as we explained in case of top down approach, and bottom up approaches, chemical precipitations, like the atoms precipitates to form nanoparticles. These are chemical precipitations. The one thing to note here is that our aim is to synthesize nanoparticles which are identical in size and composition, which have identical shape and morphology, and which are monodispersed. Why are they required? Because we have to engineer materials at a nanoscale. And if there is non-uniformity in the nanoparticles alone, how will the material be engineered, or how will the material be engineered, or how will the material have the have shows uniform property in the bulk range? So the composition, the size, the shape, and morphology of the nanoparticles in the nano range should be uniform, so that the properties which they will show in the bulk material or in the macro range will be uniform. But this is quite difficult to achieve. This synthesis of nanoparticles with identical shape, composition, and morphology, as well as containing no chemical heterogeneity, is very difficult to achieve in case of nanoparticles. Because, as you know, the nanoparticles have high surface area to volume ratio. The surface area of nanoparticles are quite high as compared to the volume. If a material has high surface area to volume ratio, they tend to agglomerate. They tend to attract to attach itself to any of the impurities there in the surroundings. To decrease the energy, everyone tries to decrease the energy. If a material has high surface to volume ratio, that means the energy is very high. They want to release the energy. They want to come to a state where they are stable. They want to always come to a lower energy state. That's why they agglomerate among each other, or they agglomerate with any of the particles which are found in the surroundings. That's why a nanoparticle having pure homogeneous composition, as well as identical shape and morphology, identical composition, is very difficult to obtain. But we are the due to the recent advances in technology, we have produced around 99 to 99.9% purity of nanoparticles. So this was all about the first session about the synthesis. To give you a brief idea about what is nanotechnology, what is nanomaterial, how can nanotechnology be implemented in case of nanoparticles, how can you engineer material properties with the help of nanoparticles, and finally we came across the synthesis techniques, and nevertheless we also mentioned about the types of nanoparticles. This was just an introduction class to show you that what is the range we're talking about, what are the different types of nanoparticles, to give you the introduction about the nanomaterials. We'll be going through more detail regarding this course in the following weeks. There is an interesting video, TEDx talk about the nanotechnology. If you have more interest to know what is nanotechnology, or how is it helpful, or how is it helping in engineering materials, or how is it helpful in material scientists, you can go to YouTube and check out this video. This is an interesting video where she talks about nanoparticles and how they are interacting, or how they are helpful in the case of material science. So this was all about the course. And if you have any doubts regarding the this session is recorded, so this will be available in YouTube for sure. And if you have any doubts regarding your assignments, and so I think I have covered most of the portion of the first week's assignment. First week's assignment was quite straightforward. It did not have any questions which are way out of the course. It was quite straightforward. So I have covered most of the things which were discussed in the first assignment. So if you still have any doubts, you feel forward to discuss with me today, or in the discussion forum which is present there. You can drop by the questions there, or we can discuss it in the next session next week, which is scheduled for next week. So do you have any doubts? Those of you who have joined, or we can end the session here. Everything is clear in case of assignments and all, or do you have any doubts? Okay, Siddharth said it's all clear. It's fine. Thank you. Thank you so much. Thank you so much, guys, for joining. We'll meet next week. If you still have any doubts regarding the course, regarding any questions, you can just ask me in the discussion forum, or we will be discussing in the next presentation. Thank you so much for attending. Thank you. Have a good evening.